Hello and welcome back to this second video of a three-part series in which I present my PhD thesis, or rather quickly go through the presentation from the defense. So now we'll go through or show one method for designing orbitally stabilizing feedback and how we can do it for various types of motions. And let's begin by having a brief overview of the method in question. So we'll now assume that we know some orbit which we want to stabilize, and in particular we'll assume that we know a particular parameterization of this orbit, also called S parameterization, due to the parameter S which is used. Now it consists of three C2-smooth mappings in the general case. So here X sub S is just the normal state curve along the orbit. Now if you recall from the previous video, orbits of autonomous systems should not have self-intersections, so we assume that XX has to be one-to-one. Likewise, we do not want its tangent vector to vanish, so we also have this additional property shown here. The reason for this is will be apparent, or will not be apparent in this presentation actually, but it can be found in the thesis as it allows us to design a so-called projection onto the orbit in question. Now U sub S, it's just a normal control curve along the orbit, and rho is a non-linear time scaling function. That is, it allows us to reparameterize time along the maneuver, so this allows us, provides a bit of flexibility, for instance, in the motion planning procedure, but for our purpose it also allows us to extend the methods we will show later on to more general types of orbits, not just periodic ones. Now, since it's a time scaling function, we generally require that it's strictly positive, except possibly at a finite number of isolated points where it vanishes. Now, such a point would correspond to an equilibrium point lying upon our orbit. Now, we of course want this to be an orbit of our dynamical system, so we need it to be consistent with the dynamics, which corresponds to this relation holding here. And notice here that we find S through this scalar differential equation, which provides this time scaling mentioned earlier. Now to just go a bit heavy on the jargon here, this means that this orbit, which is traced out by the curve XS, is a one-dimensional controlled invariant embedded submanifold, in general at least. So if we have an equilibrium point, for instance, then it would be zero-dimensional, and it's also possible to have slightly higher dimensional attractors. But for the purpose of the thesis, we mostly just consider one-dimensional types of orbits. Now the task we will now consider is essentially to generate some forward invariant tubular neighborhood enclosing or around the orbit in question. So if we have our orbit in black here, we want to generate by feedback this blue shaded region, which is forward invariant, which means that any solution of the system entering into it will remain within it. And preferably we also want to ensure that all such solutions contract to the orbit at a given rate. So perhaps exponential is the general case in the thesis. Now the reason we only consider generating such a tubular neighborhood, so not a huge neighborhood giving a very large region of attraction, is mainly due to the task we are looking to solve. So if you remember from the last video, we had a look at a backflip, for instance, so I'm not claiming that I have solved that problem, but for such tasks, generally having a large region of attraction, something like global stability, for instance, does not really make sense. Local is the best one can do. And if you want to enlarge the state space, it's probably better to add more trajectories filling out, each with its local controller, generating such tubular neighborhoods. Now the nice thing now with that justice requirement, that since we know an orbit, we know that this corresponds to some normal motion of the system, which consistent with dynamics, does not violate kinematic constraints, go beyond actuator saturations, does not collide, and so forth and so on. Then if we remain within this tube, then we should not violate these constraints either, most likely. So having these local controllers, ensuring that the states may remain within them, is essentially the perfect way of solving the problem we are looking to solve. And the nice thing now is, since we have knowledge of an orbit, that is, we have knowledge of what all of the system states are when they evolve along it, this means that we can linearize along it. So before we go on to show how the linearization is used in thesis, let's give a bit of a reminder of how linearization is used to design feedback for nonlinear systems. Since we assume knowledge of an orbit and a particular parameterization, we can generate from this a nominal trajectory which we can linearize about. So doing so, for the nonlinear system, we obtain the variational system shown here. Now here I use this delta x notation to denote the state of this linearized system, and it might be considered like an infinitesimal perturbation away from the normal trajectory. Now in the case that our trajectory was just an equilibrium point, so a trivial orbit, then this would be a linear time invariant system. And then it's well known that if this linear time invariant system is stabilizable, then we can generate a feedback stabilizing its origin or its zero solution, and the same feedback from which we can utilize to design an exponentially stabilizing feedback, in fact also for the nonlinear system. There are various ways of doing this. So for instance, you can solve Riccati-based equations, or like FQR type of methods, or as shown here, you can solve linear matrix inequalities on LMI. And if you find a solution, for instance, to this LMI, then you can take, for instance, control law shown here. And I should mention you can solve this LMI using semi-definite programming, for instance. So you define feedback here. E is just the difference between your current state and the equilibrium point, and K is defined from the solution of the LMI. And this feedback for the nonlinear system, it would render your trivial orbits on equilibrium point exponentially stable. And from it, you can construct a local but strictly optimal function for the equilibrium points or the trivial orbits. Now, of course, these are only local results, but they are quite general procedure which is applicable for a large class of nonlinear systems, and from which can provide a seed to utilize more other types of methods. You can utilize it to construct a conservative, perhaps, but estimate of region rejection and so on and so forth. But this is equilibrium points. What about more non-trivial orbits? What about periodic orbits, for instance? Can we utilize similar techniques? So for one, if we will linearize about a periodic orbit, then this would be a linear time-varying system. And to stabilize its zero solution, then we would naturally need a time-varying feedback, and this would violate the orbital stabilization problem. And in fact, it also turns out that if we have generated beforehand feedback which exponentially orbitally stabilizes this periodic solution we want to stabilize, then in fact this variational system, its zero solution, will not be asymptotically stable. I'll only go through this briefly, but essentially this can be shown using, for instance, the Andronov-Witt theorem. So if you design such a feedback, this exponentially stabilized orbit, then this zero solution of this system will not be asymptotically stable. Only a subspace of dimension n-1, so one less than this dimension of the state space, will in fact be stabilized. But since we are linearizing, or we want to stabilize a periodic orbit, we must have these directions in which these directions in our state space which do not contract to a point, and hence we must have that this system has one zero characteristic exponent. So we cannot utilize this regular linearization to design orbitally stabilizing feedback, at least not directly. So we need a different type of procedure to allow us to utilize similar linearization-based techniques to also design orbitally stabilizing feedback. In order to allow us to find such conditions for designing orbitally stabilizing feedback utilizing linearization-based techniques, we need to introduce some concepts. So the first is a so-called projection operator. So this is a scalar function, generally assumed to be C1 smooth in its domain, and it should satisfy this left inverse property from some S parameterization. The nice thing with this, that's using this projection operator and the curve XS, we can define a projection onto the orbit in question through this composition shown here. Now, with such an operator in mind and this projection, we can, for instance, ask if we take some points on the orbit, so for instance shown in red here, and we ask what is the set of points in the vicinity of the orbit which are projected onto this particular point on the orbit through this projection operator. Now this will trace, this set will correspond to a hypersurface, a so-called moving Poincare section, as was coined by Leonov, which is locally transverse to the orbit. Now the reason it's called a moving Poincare section is that if we slightly move or continuously move this point, then the whole surface or section will move along it as well. And for those familiar with Poincare sections, then it's essentially the same concept, but now we allow it to evolve along the whole orbit. And the nice thing with this is that if we take some particular point on this section, or on the moving Poincare section, now it projects to this corresponding red point. But from this we also have a sort of a measure of the distance from the current state to the orbit itself, which you can denote by E. And if we can assure that for all states in some vicinity of the orbit, this value E is driven to 0, then naturally this corresponds to contraction to the orbit or to orbital stability. Asymptotic orbital stability, in fact. So what we essentially are, these E's they are projection-based excessive transverse coordinates for the orbit in question. Transverse as they evolve upon this moving Poincare section, which is locally transverse. They are an excessive set of coordinates, as they have naturally n elements, whereas they evolve upon the moving Poincare section, which is a hypersurface, so it's has dimension 1 less than the dimension of the state space. So in theory, we could find a minimal, or you might say, set of transverse coordinates. So these would be local coordinates upon such a moving Poincare section, denoted by Z bar, for instance. And we could utilize the same that if we drive the value of Z perp perpendicular to 0, then we have asymptotic orbital stability. Now there are methods for introducing such coordinates for various types of systems and orbits, but in general it will often be a bit tricky, might require numerical methods and the like. But you generally, in order to design an orbitally stabilizing feedback, at least for underactive systems, you will generally need to utilize some projection operator. So, since you need it, why not instead utilize this E instead of a minimal set of transverse coordinates? But this brings with it a bit of a difficulty, namely that these are excessive coordinates upon the moving Poincare section, which makes finding or linearizing their time evolution a little bit more tricky. But this problem with the, you might say, excessiveness of these coordinates is quite easy to handle by just spotting that if you compute the Jacobian of this E viewed as a function of x and evaluate it at points along the orbit, then it, we define it here as this calligraphic E perp, then it provides a projection onto the tangent space of the moving Poincare section about the point on the orbit. So this blue shaded section shown here. And this we can utilize or use to allow us to use linearization-based techniques to design orbitally stabilizing feedback. So before we show that, let's just briefly look at how the control structure looks like for such a scheme. So if we have our dynamical system shown here in green, we assume measurement of all of the states. Now the projection operator, from it, we then compute the states and in a sense retrieve the corresponding parameter S to be used in the feedback later on. So from it we can, for instance, compute the normal control curve along the orbit. There are other expressions which can be used here, but this is perhaps the most generic one. The design can construct some sort of feedback to stabilize the orbit, and if necessary, if we have unknown perturbations or disturbances or uncertainties, we can, as we'll see in the next video, also design a robustifying feedback extension to enhance robustness, utilizing, for instance, sliding mode control. But we will look now at how can we design this K inside here, which ensures exponential orbital stability of solutions. For this, we need, as we mentioned, we are looking at linearization-based techniques. This, and I should mention, we also look at periodic orbits now. We derive the first order approximation of the time derivative of this variable E. Now, unlike the variational system we saw earlier, which was a linear time varying system, this provides us with a set of differential algebraic equations, as we have this additional so-called transversality condition. This just occurs that since these are the first order approximation of these excessive transverse coordinates upon a moving Poincare section, this requires that they should evolve upon the tangent surface or the tangent surface of the moving Poincare section about the point on the orbit. Now it's not there just for show. if we in fact removed this equation and only looked at this differential part of the equations, it turns out that this equation is not stabilizable. But it might be with the transversality condition. So if we want to design an orbitally stabilizing feedback utilizing these equations, we need to account for this transversality condition somehow. But we can utilize this Jacobian we saw earlier for that. So if we have a periodic orbit, much like we saw with the equilibrium point, if we can find a solution to now the projected differential LMI, or for that matter a Riccati-based type of equation, then we can design exponential orbitally stabilizing feedback for the nonlinear system as well. And the way now this transversality condition is accounted for is utilizing this matrix multiplication here, which essentially means that we only need this equation to hold on the subspace where a transversality condition holds. Where it does not, with this subspace we can neglect. So if we can find such matrix functions w and y with these properties and having the same periodicity as the periodic orbit, or parametrization of it rather, and we can solve this equation using, for instance, semi-definite programming, then for the nonlinear system again, we can take this matrix function k, defined through the solution of the projected LMI, and we can utilize these excessive coordinates as shown here to design feedback, and it, much like the equilibrium point, will render now the periodic orbit exponentially stable, and it provides us with a local but strictly optimal function. Again, local results, but methods which are highly applicable to a large class of nonlinear systems, and from which we can build more advanced methods if need be. Essentially what we have done now is that we found this local strictly optimal function. And what if we construct such a tubular neighborhood given by some interior level set of the function? Now, from the conditions on the last slide, we saw, or we ensured that we had that this the time derivative of this function was exponentially decreasing with some upper rate lambda. Now v was defined in terms of the solution to the differential or projected differential LMI, this w. But essentially, if we did not have any necessary or requirements upon w, other than being, say, positive definite, then in a sense this requirement here could be ensured by having w, the inverse of w, going to zero larger, faster than the variables e. But on the last slide, what we did was we had a periodic orbit, and then due to the closeness of the orbit, we can ensure that this decrease condition ensures, in fact, that we have exponential orbital stability of any solution upon the orbit in question. But if we can then replace this condition of having the orbit closed with alternatives, then we can utilize similar ideas to also design exponential orbital stabilizing feedback for other types of force motions as well, not only periodic orbits. Okay, so this brings us to the next part, which is how can we design orbitally stabilizing feedback utilizing these techniques for other types of motions as well. So we look at two types, so-called point-to-point maneuvers and periodic orbits of hybrid dynamics. The first are so-called point-to-point maneuvers. So we start with the system at rest at some forced equilibrium point, and we want to drive the states along some orbit or pre-specified curve in the system state space, and make them come to rest at some other equilibrium point at the end, denoted x omega. Now for this we naturally need to make some updates to S parametrization, so the endpoints of this curve xs should be the equilibrium points, the forced equilibrium points. Since these are equilibrium points, we want this time-scaling function to vanish at this point, but it should be strictly positive everywhere in between. Now we also need to make some updates to our projection operator in this case. So within some sort of tubular neighborhoods like this blue shaded one, then we want the projection operator to act just as it did for periodic orbits. It should define moving Poincare sections, so this surface pi shown here. But we also need to account for these equilibrium points. So within some regions, for instance like this red shaded and this green shaded half ellipsoids, we want the projection operator to project onto the point corresponding to the equilibrium points therein. Now, having such or making such a modification to the projection operator, it's no problem finding such operators, but it comes at a price in the sense that we lose the smoothness of the projection operator within its domain. So we cannot ensure that it will be, for instance, Ceto smooth, but we can ensure that it will be locally Lipschitz within its domain, in the sense that it will only lose this smoothness when going from, say, this blue shaded region into the red or the green one, or vice versa, where it needs to lose its smoothness. There's also a bit of another caveat with the approach in the thesis. This comes mainly from trying to make the statements as beautiful as they can in a mathematical sense. And this is that we will consider only these time-scaling functions rho, which are continuously differentiable. This means that the convergence to the end equilibrium point, or the divergence away from the initial equilibrium point in particular, can be at most exponential. So this means that when trying to move from this initial point away from this initial point along the orbit here, it will in theory take infinitely long to actually go away from it. So it makes perfect sense from a mathematical standpoint, and that's why we have stated it as we have done. But of course, from a practical point of view, this is not a very ideal trait of your controllers, but it's quite easily avoided by some modifications which you can find in the thesis, or you can also allow rho to be non-Lipschitz continuous, for instance, away from the initial equilibrium point. So you can have this finite time divergence away from it, as opposed to infinite time. Okay. So let's show when, provide conditions for when a feedback of this form will in fact orbitally stabilize such a type of motion, so such a point-to-point maneuver. Essentially what we are asking is, when is it true that the final equilibrium point is asymptotically stable, or that the corresponding orbit, so this or the whole point-to-point maneuver, when it is it exponentially stable? The final equilibrium point is, in a sense, the end point of the orbit, and so it is asymptotically stable relative to this orbit O. So we can utilize a reduction principle to show that B implies A. So in that sense, we need to only find conditions ensuring that B holds. Now this is not too difficult either. So essentially, if you can find some sort of matrix function, C1 smooth matrix function L, and some numbers such that this function B, defined as follows, satisfies this exponential decrease inequality for almost all states within some interior level set of this function V. So by almost all, it means essentially that it cannot hold on this on these sections where the projection operator lost its smoothness, as we saw earlier, due to the projection operator we used here, but it should hold everywhere else. So if we can find such an L, then we can show that for a given k, this feedback will in fact be render the orbit exponentially stable. Now, sufficient conditions for the existence of this is essentially that if you can find a solution, so we could define this L perp as shown here, which satisfies this projected differential Lyapunov equation, projected due to these Jacobians we saw earlier on, multiplied from both sides, so we only look at a particular subspace, and this L also satisfies at these boundaries a pair of algebraic Lyapunov equations, shown here. Now these are such that if we, for instance, took this P and fixed that it only projected onto a point corresponding to one of the equilibrium points, then these solutions to these algebraic Lyapunov equations would then ensure that this would render this corresponding equilibrium point locally exponentially stable. So essentially what we do is we merge through, or we take a controller which in a sense merge these controllers which render each equilibrium point locally exponentially stable, together with a controller which stabilizes the transverse directions in these tubular neighborhoods, and we do so continuously through the projection operator. Let's look at an example of this in practice, so-called maneuvering a ball upon the so-called butterfly robot. So this is the butterfly robot. This is figure of H-shaped robotic hand here, which we have a torque provided at this center point. And upon this, so you can rotate the hand, on it there is a ball which you only can indirectly influence through its contact with the robot hand. The task is to take the ball from being at rest down in this well region and then move it along a particular orbit to come to rest, so it's curve in state space, to come to rest as this final configuration shown here. So let's look at some simulation results. We have also had some preliminary experiments, but some equipment failure has not allowed us to show full working experiments yet, but hopefully soon. So we see here it swings up the ball to the desired position without it departing from the frame. And you can also add some perturbed initial conditions, uncertainties in the mass of the ball, some disturbances and noise and so on. It still works pretty well. Okay, so this was point-point orbital stabilization of point-point maneuvers. Now let's have a look at stabilizing periodic orbits of hybrid dynamical systems. A hybrid dynamical system is a system which has continuous phase phases of continuous dynamics together with regions in the state space in which the states undergo these discrete jump events. So in our case, we want to start at some, or not necessarily start, but we want to have an orbit which, starting on some of these switching manifolds, sigma sub plus, at the point xa, the states evolve along a predefined orbit, then hits the corresponding switching surface sigma minus at the point xp, and then are mapped directly back to the point xa through this jump map. Now the methods also allow you to have like a certain sequence of such jumps before you have a closed jump taking you back to the start point. But for the purpose of simplicity, we only look at this single loop shown here. Now again, we need to make some updates to our S parameterization, so this curve XS should correspond to these endpoints, so I think A for after and B for before the impact, before the states hit the switching surface and are mapped back. This time we have no equilibrium points, so rho should be strictly positive, and we also want these transversality conditions to hold, in the sense that we do not want the orbit to have a grazing impact. So we wanted to hit it, the switching surface with some non-zero angle. Now the method we will use is quite similar to what we used for the point-point maneuvers, but we need to take into account a bit of a difficulty, in the sense that if our moving Poincare sections now do not align with the switching surfaces, then utilizing linearization-based techniques is not straightforward. I won't go into much detail, but essentially what we can do is we can utilize a certain set of projections between the moving Poincare sections at the ends onto or from the corresponding switching surfaces and back, together with Jacobian of the jump map. We can define this projection matrix shown here to allow us to account for the scenario if these surfaces do not align. And this similar procedure can be found in this paper shown here. So with this jump map matrix, this JPrepare, we can state a statement quite similar in some sense to what we can use for point-to-point maneuvers and the like. And what we do is we have some projected differential LMI as shown here, together with an additional condition to count for these jumps at the end of the cycle. If you can find solutions, so W and a Y satisfying this specification for some very small mu, then this feedback shown here with K defined will render the hybrid periodic orbit asymptotically or asymptotically stable. Look at a simple example, the so-called stabilizing symmetric gates of a biped robot. So we have generated a stable and energy-efficient walking gate, here walking with a step length of half a meter. Now this three-link biped, it has 3 links, but it has only one actuator between the legs mounted at the hip. To account for this low number of actuators, so it's 2 degrees of underactuation, we have added a pair of linear springs between each leg and the torso. So the next we'll see how the orbital stabilizing feedback. So the first we start with perturbed initial conditions, so this is in closed loop. We see that gradually swings in and before it, after a few steps, settles onto the desired gate. And keep in mind it has only this one actuator. But if we start also with different initial conditions, even though we see that it manages to settle down and converge to the desired orbit, we see that we get this large spike here, so it has some sensitivity to with respect to initial conditions or perturbations. But by just adding saturation, we see that it can still handle the same initial conditions and still manages to stabilize the gate, even with these quite restrictive saturations. And as we have also shown in simulations that it is quite robust to uncertainties in system parameters and the like. Okay, so in the next video we'll have a look at robust orbital stabilization utilizing sliding mode control. Thank you very much and hope to see you then.